Okay, thanks. Okay. Yeah, you'll also be able to access the recordings on the Canvas later. So if you missed any class, that's also fine. You can go back and you can access the recordings. Also, like after the session's over, you'll still be able to access the recordings for like a few weeks afterwards. So really no rush. Definitely try to make class in person, like if you can, or like in person. Like try to make class like the time if you can, but if you can't, you can always make up lectures later. But yeah. So I gave the spiel earlier before the recording, but if you're watching the recording, my like session or like lecture primer is really here to kind of like supplement or kind of like motivate some of your reading. If you haven't done the reading for this week yet, that's like perfectly fine. The course is just starting. But for the most part today, we're going to be talking about chemistry. Um, uh, I think you should try to get your readings done like as soon as possible. But also, I think my course, or at least the way I teach lecture primer, you can definitely walk in like not really knowing anything. And now that you've like heard it once or you've just like been exposed to it through class, then like maybe the things that you read will make more sense, right? Also, feel free to come to class if you have any like questions. Um, if you have any class, like if you have any questions or any like clarifications you'd like for the material, like feel free. But yeah. Yeah, so I'm a sophomore at Harvard. I'm studying like biostatistics now. I'm an old head. I took when I was competing in USABO, I competed between 2021 and 2024, and I took the initial class in 2020. You can see here's a picture from USABO camp back when it was still in Virginia. Now it's at Harvard, so all the more reason why you should try to come. Actually, I think yeah, any if there aren't any campers in the class today, which is possible, I may be able to see you guys like during camp this year. I think camp is at Harvard again. I'll be at Harvard over the summer. I just put this picture in because you can see Vishal over here. He's really balling out over there. But yeah, Vishal's super funny guy, and you guys will get to see him soon. Okay. Does anyone have any questions so far about like, just the course logistics? I know it's the first week, so there's a lot of stuff. If you're new to the course, like what you should do, like any questions or any like overall like this is the obligatory like first class. Here are the logistics. Here's the syllabus. Here's what we're doing. But yeah. How old was Freddie? Freddie is he's a sophomore in this photo. Yeah, he's a sophomore. Um, when would be the best time to do the reading by every week? Yeah, so definitely at least finish the readings by like the main lecture on Saturdays. But you may find that like doing the readings will help you for like the homework for that week. So I think just like as soon as possible, I think your hierarchy should be like do the readings first and then do the homework and then do the like class is what I would say. What's the reading for this week? Chapter 2 of Campbell. That's it. Campbell. Sorry, I don't know why I said it like that. But yeah. Yeah, chapters 1 and 2. Yeah, chapter 1 is, you can, if you don't read it, I won't say anything. Not too necessary, but like, yeah. Yeah, so okay, yeah. So I guess the way this works is kind of what I teach is kind of like a week in advance. So what I'm teaching is like what Kevin will cover next week, right? So I'm here kind of to like give you like a sneak peek or a preview of like the material. And so for that reason, this class will be like a lot more casual, a lot more chill. I'll definitely like take the difficulty down a notch. But I'm here just to make sure like we're all on the same page so you can understand what Kevin's talking about during lecture. Right. Oh, okay, great. Great. All right, let's chill out. Let's chill out on the glaze here. Let's chill out on the glaze. Okay, I think we spent enough time talking about logistics. So, without further ado, we can just like jump straight into the content. New concepts too. I don't know. I actually disagree. I've talked to Kevin about this, but I strongly think that like the most value from this, like value, if you're talking value specifically for like prepping for USABO, I think that you don't need all the bells and whistles. I think it's like perfectly reasonable to make it to camp just like knowing your fundamentals, right? Just like knowing Campbell through and through, and like at a very high level, I think is like good enough. You don't need to know like all like the little like nitty-gritty details about like exactly every like detail in biology, right? There's just like statistically it's a small chance that it's going to be tested on. Whereas like if you just know like the general topics that are important and like are very familiar and you'll like never make a mistake, I think it's like very important, right? That's why I think it's always good, even if you're like a multi-year, if this is like your second, third, fourth year like preparing for USABO, I still think there's value in going back and reading Campbell, right? Like if you've truly read everything, I don't think you should go and read like I don't know, like Fotoima for like for no reason, right? I think like at least like skim through Campbell like once a year. I read Campbell like 4 years, like oh, sorry, 4 times, once like every year, right? But yeah. How many times? Yeah, like 4 times, I think. Maybe a little, maybe more. I mean, obviously, like not like cover to cover, like maybe like by like my fourth read, I would just like skim through some of the chapters that I found more interesting and like skip over the ones that I felt like I had a good grasp on. But like I at least like went through like 4 times in a row, right? Nice, Adarsh. That's pretty good. What about chapter 1? Kevin covered chapter 1 already on Saturday, so there's not really any need for me to like recap it, right? Like I'm the primer. I'm not like the recap. I'm not like the YouTube recap like series. like brain rot channel. Um, yeah. Great. Okay. Yeah, I'm seeing a lot of familiar faces in the chat, but also seeing a lot of new students. So welcome, Biology, great community. I personally endorse it a lot. I took the first season and I thought it was super helpful. I think the main thing is that it's very structured. It's very easy to feel overwhelmed with like the amount of content. There's like a whole textbook and there's maybe like three textbooks you need to read. But I think if you just like follow along with the course, it's very like low effort, not low effort, but like very low activation energy to just like go along with like the flow of the course. Right. Okay. But yeah, unfortunately, I only have 1 hour. Kevin has 2 hours, so he has plenty of time to waffle about. But I only have, I have a lot of content. I think I have like, how many slides do I have? I have a lot of slides. Oh, nice. I have 69 slides to get through. So we got to go like pretty fast. Oh man. Oh, my hair is like really long. I look, you need a haircut soon, but I think I'm just gonna thug it out until I finish my finals. I look, you don't have time. Okay, great. Without further ado, in the beginning, the universe was created. This has made a lot of people very angry and has been widely regarded as a bad move. This is a reference to a sci-fi novel that I like a lot. But you remember the slide? Great. Okay. I did not change the slide. I think the slides are exactly the same. This is the same slide. Okay. And so, in the beginning, there were just the elements. And elements combine to form chemicals. So what is a chemical? A chemical is really just like any compound formed of like it can be either just like one element or like multiple different kinds of elements. Right. So, to the people who like, oh, I don't like them like putting chemicals in the food and like chemicals in the water, like, from a scientific standpoint, that doesn't make any sense because like food and water are like actually chemicals. Right. And so here's some examples of like the most common elements in the human body. So you can see for the most part, it's going to be like oxygen, carbon, hydrogen, and nitrogen. Can anyone tell me like, maybe what are some kind of molecules you may have heard of, or like some like chemicals, for example, that you may have heard like these are originating from? Right, exactly, right. Like these are all like household names you've heard of before, right? Like water is made of like H2O. Exactly, like your sugars, like nucleic acids, right? Proteins are all made of these like fundamental building blocks. And you can see that just these four elements occupy 96% of like the human body. The human body is actually a pretty representative sample of like most like animal like living tissue. If you were to like put a human into a blender and like blend it down to its like atoms, and you like took like a mouse or like a monkey or something, you'll find basically almost the same like distribution of like elements. Maybe there's like some slight differences between like plants and animals and fungi, for example, but for the most part, this is pretty representative. How can plants live without calcium? Plants actually do need calcium. Not to the extent that humans need calcium, but yes, they do actually like function with calcium as well. I don't think it's like, yeah, I think it is like necessary. I'm pretty sure it's like necessary. Anyways, yeah, the other elements are all basically going to be considered like, not like trace elements, but kind of like micronutrients because they occupy like a relatively small amount of like body mass. You can see that this is weighted by like molecular mass, right? Like total mass of the body. But if you were to actually weight it instead of mass by like atomic or like not atomic number, but like number of atoms, the majority of the human body is just made up of a bunch of hydrogen atoms, right? Like basically saying like if I were to take like a random like atom from your body, like 63% of the time it would just be hydrogen. And the reason why it's kind of like underrepresented here in this is because hydrogen is so light, right? So you can see like proportionally like why the majority of the human body is like made of oxygen. But yeah, okay. Next, we're going to talk about the periodic table. So if you were a chemistry student, you'd have to memorize like all these different atoms, like the P block, the D block, and like the S block. But because we're biologists, that's too much. That's too much. We have to memorize everything, right? So we got to simplify it down. This, for all intents and purposes, is your periodic table for like USABO. Maybe if you're like mega tryhard, you'd be like, oh, like the iron's over here, and like there's all like these other trace elements. But for the most part, most of the biochemistry we're going to be talking about for this course, or at least like for the first half of this course, are going to be based on these like smaller atoms, very light atoms. There are like two main reasons why life is mainly using like these like very light elements. You can see at the top two or top like 2 to 3 rows of the periodic table. Can anyone tell me like maybe intuitively like what's one of the reasons why like life predominantly uses these elements? Yeah, one of them is like okay, yeah, sure. Actually, that's not one of the ones I thought of, but yes, electronegativity is a good one. Yeah, so Udeep said they're electronegative in general. Yeah, so electronegativity increases as you go like up the periodic table, right? So like these ones are more electronegative, so they're kind of more like active, right? Jay says, yeah, Jay says it's because the Big Bang made light elements. Exactly, right? So, first of all, like the most common element in the universe is hydrogen, right? And so, over time, like as the universe like created more and more elements, we made some of these like slightly heavier elements. But for the most part, these like heavy, I hate having to switch back and forth, but for the most part, like all of these like heavy elements are like quite rare, right? So intuitively, it just doesn't make sense. Like if like life needed, for example, like a ton of like polonium, right? Like you're just not gonna be able to find it, right? So life just works with what it has, and it happened to have like a high abundance, especially like within the Earth's crust, like all these elements. The second reason is kind of like related to What are people saying? Yeah, chemical properties, kind of exactly right. So another thing is that life is like pretty dynamic, right? There's a lot of things that a cell has to do. A cell has to like metabolize. It has to like take in energy. It has to like produce some molecules, right? And this is all kind of facilitated by being like very light and nimble, right? Typically, like these smaller elements are going to be like lighter, like physically like lighter, and so they're able to like jostle around a lot more, and they're kind of easier to work with, right? It's kind of like you'd rather herd sheep than like herding like elephants, for example. That's kind of like the analogy I would think of. But yeah, I think those are the two main reasons why, like kind of like the chemical properties, but also like the abundance is the most important things. The periodic table is organized. I guess I should explain how this is organized, but you can see on the top here, this is the atomic number. If you've never seen this, atomic number just refers to how many like protons are in an atom, right? So, for example, if I added an electron to this hydrogen atom, it's still going to stay a hydrogen atom, right? Because it's still fundamentally just like one proton, right? So it'll have two electrons but one proton, so it's just like a negative like hydrogen ion, right? That's actually why there's also things called like isotopes. So isotopes of elements are when you have like multiple neutrons. So for example, like if you've heard of like carbon 12 versus like carbon 13 and carbon 14, they're all still carbon atoms because they still have like six protons, but they may have anywhere from 6 to 8 neutrons depending on like what isotope it is, right? And if you're that's also like necessary in like biology for later. Yeah, so the rows indicate kind of what are called like electron shells. So without getting into too much physics, like an atom is made of like a nucleus, which is made of like protons and neutrons, and has like an outer electron shell. Typically, they're going to be drawn in textbooks kind of on the right here. It's just like these nice like concentric rings, and that's like a very good like easy mental picture to have. In fact, right? Like you can see here, they're drawing these rings. In reality, electrons aren't really just like they're not really like specks. They're kind of like very strange. They're kind of like waves is the way you should think about them. So really they're going to be like this cloud of like a negative charge around an atom. But for the most part, you can see that these clouds are going to be distributed in these kind of like orbitals. Where do these orbitals come from? Don't need to worry about for USABO. If you're interested, you want to learn more like physics, feel free to. But for the most part, the intuition you can have is kind of like these are just like waves. So if you ever watch like a YouTube video where they have like a plate and they bow it with like a violin bow or something, and you can see like these standing waves. That's actually what generates like what these orbitals are. And for the most part, you can see that like these higher energy orbitals kind of have like more like vibrations. Like these orbitals will come in like these different shells. And the main thing that's important to know about these shells is that they're not like classical shells, right? You can have like, for example, like if you want to talk about like height, right? Someone can be like 5'9", someone can be like 5'9.5", someone can be like 6'1" or like whatever like possible height. But electrons, they only come in discrete like energy shells. And so whenever energy is going to be absorbed or released between moving these shells, it only comes in these like exact like intervals, kind of like steps on a ladder instead of like a big like ramp. The lowest energy shell is going to be called the 1s orbital, and this orbital will hold 2 electrons. And then the next orbital is going to be the 2s and like 2p orbitals. Each orbital will hold 2 electrons. And so because there's 1s orbital and 3p orbitals, you're going to have 4 total orbitals for the next level, so it's going to have 8. In like maybe your honors chemistry class, you've ever heard of like the octet rule. That's where the octet rule comes from. It's because these electrons, these atoms want to be in like the most stable configuration possible. And the most stable configuration they can have is to have like a full shell right here. And so you can see as you move across from left to right across the periodic table, you're going to see more and more electrons until they're completely filled. And as you move from top to down, you're going to see more and more shells that are going to be completely filled. And so that's actually what causes, that's basically all like chemistry is. All chemistry is basically the study of like how electrons interact between different atoms, right? What makes a full shell more stable? That's a great question. It's like I can give you like the hand wavy way, but the true actual like why is like more of a quantum mechanics answer. It has like more degenerate energy. Anyways, we'll talk about bonds in a bit. Don't worry about bonds yet. Great. Okay. Any questions about the fundamentals of what atoms, like electrons or electron shells are? I don't think you need to know it to this detail for USABO, but just so we know what we're all talking about, like what does it mean to like add an electron to like an atom, right? That's like what it means. Okay. Thanks, Kevin. Wait, Kevin, I took a quantum class last year. I have to use it. Like, what am I paying all this tuition for if not to like teach it? You know? Oh, that's Joseph MB, MB, MB. Fuck. Okay, I didn't realize it's actually. Oh my. All right. Anyways, okay. Bonds, right? Okay. So obviously, this is like, this is some pretty interesting dynamics, right? But if all of like matter is just like these single atoms like moving around is not a very interesting picture, right? And so here's where bonds come into play, right? It's very hard to just like get a whole electron and like steal it from somewhere else, but it's very easy to kind of share electrons here, right? And so actually, here's the first example. So this is an example of what's called an ionic bond. And so sodium has like one extra electron that it doesn't want, and chlorine is missing an electron, right? So the easiest thing they can do is sodium can just like basically hand over an electron to chloride. And so sodium has a full shell, chloride has a full shell. But now, because the sodium atom has 10 electrons, but it has 11 protons, it's going to have a slight positive charge. And vice versa, the chloride is going to have, I believe, 17, yes, 17 protons and only and 18 electrons, right? So it's going to have a slight negative charge. And because they have this positive charge and this negative charge, they're going to be electrostatically attracted to each other. And they're going to form what's called an ionic bond. This actually generalizes into having like multiple like sodium and like chloride ions. And so like macroscopically, this will form what's called like a crystal, right? And sodium chloride, if you ever know, this is just like table salt. And so table salt is an example of an ionic compound like formed in this ionic bond. So this is kind of like an extreme example of electron sharing, right? Where like basically the sodium just like hands over the electron. But you can also have what are called covalent bonds, where they kind of share the electrons equally, right? So the easiest are, for example, like diatomic hydrogen and diatomic oxygen. So hydrogen, each atom has one electron and wants two electrons. So they just share one electron with each other, and they can form this like single bond. Oxygen, they want two electrons, so they're going to share two electrons each, and so they're going to form this double bond. You can form covalent bonds between two different atoms, right? So H2O is like an oxygen single bonded to two hydrogens, and then methane is like carbon single bonded to like four other hydrogens because carbon wants like four electrons. Great. Covalent bonds are kind of drawn very simply in just like kind of these like ball and stick models. But again, because electrons aren't actually like discrete like particles, right? The way you should think about them is it's kind of this like cloud of like electric charge, right? And because oxygen is like very strongly electronegative, whereas hydrogen is not as electronegative, the electrons will spend more time around the oxygen atom. And so this is going to lead an overall like negative charge like on the oxygen side and a positive charge towards the hydrogen side. And these can actually form what are called hydrogen bonds. So hydrogen bonds is like an electrostatic attraction between the positive side of one hydrogen and the negative side of another oxygen. In contrast, you have what are called nonpolar bonds. Nonpolar bonds, as the name implies, don't have any kind of polarity because like carbon and hydrogen have very similar electronegativities, right? And so the electron is shared like pretty evenly between the two, and so they don't form any of these like hydrogen bond interactions. Yeah. Okay. On the note of these like attractions between molecules, we have what are called IMFs or intermolecular forces. These are extremely important, not just like in chemistry. This is actually what causes all of the macroscopic like properties that we see. For example, like melting point and like boiling point and stuff. These are related to like IMFs, but also like biologically, these are important for the interaction between like these like molecules, as we'll talk about in a bit. Yes, impossible mission force, also IMF, very funny. But on the left side here, we have what are called van der Waals forces. They're also called London dispersion forces. But basically, you imagine like a atom with like a distribution of electric charge, like purely by chance, like some of the electrons may be distributed on like one side versus the other, right? And if it is like distributed like more on one side than the other, then there's going to be like a slight polarity on one side, and this can induce like a polarity on like the neighboring atoms, right? And so if you bring any two atoms together, even if they're perfectly neutral and they're non-polar, they actually have like a very slight attraction to each other, right? And so biologically, this is important, both on the micro scale, like on the molecular, but also on the macro scale. So for example, like if anyone knows about geckos, the way geckos actually like stick to walls isn't they don't like excrete like glue, or they're not like Spider-Man or anything. They actually like have like this very strong surface area that brings like their toes like into contact with the wall. And this like van der Waals force actually like holds them onto the wall. Which is very cool. Yes, Campbell reference. It's almost like that's the reference text for this class. It's crazy. I heard something new that is not primarily LDF, and there's dipole. I mean, I think it's probably a combination of both. Like, this like sounds reasonable to me. Like, but it's probably like hydrogen bonds, if anything. That's what I think. But yeah. Okay, next, this is like a hydrogen bond. So hydrogen bond is an example of what's called a dipole-dipole. It's like a specific example of like a dipole-dipole interaction. But a dipole-dipole interaction is just when you have like two polar molecules, and like the negative side is going to be attracted to the positive side of another. Hydrogen bonding just happens to be like a very strong example of like dipole-dipoles. But you can see they are in increasing strength, right? So from dispersion force are the weakest, all the way up to like ion dipoles. So, as the name implies, it's like an ion being attracted to like a polar molecule. But you can see the strength of these intermolecular forces can vary over like several orders of magnitude, right? All the way from like 10 to the negative 2 like kilojoules per mole, all the way up to like 10 to the 2 kilojoules per mole. Yeah. Any questions so far of what we've talked about? Great. Okay, this is all like honors level chem or like maybe AP level chem if you've like taken it before. So this should be like pretty familiar to many students. But anyways, okay. Great. Okay, molecular shapes, right? So now that we're working with some kind of like slightly more like complicated molecules, right? What is actually going to give these molecules their shapes? So electrons are negatively charged, and so for that reason, whenever we have these like electron bonds, they're going to want to like repel each other. Right. And so, for example, if you have like one atom bonded to two others, the easiest way or the way you can keep them like furthest apart is to just like spread them out in like a linear shape. Right. And so, as the name implies, this is called a linear like electron geometry, or like a linear like molecular geometry if you have like two atoms here. If we have three electron bonding domains, the easiest way to split them out is now you have them like out in this plane in this like kind of triangle shape. And so the electron geometry is going to be called a trigonal planar. And depending on how many atoms you have, so for example, here's like boron bonded to three hydrogens, you'll have a hydrogen in each one, right? So that's a trigonal planar. But another example is this like, I don't know what this molecule is, but like oxygen is like, sorry, water is like an example of this, right? They have a lone pair here, which kind of like represents like a bond, and like oxygen and then two hydrogen on each side. And so we observe this kind of like bent shape instead of it being linear like that because there's a lone pair. Yeah, so the way you look at it is, so electron geometry refers to the total amount of electron domains, and the molecular geometry is like how many like actual like atoms there are, because there may be lone pairs that like you like, don't observe, right? Yeah, this is called Vesper, or valence shell electron pair repulsion theory, I think. But yeah, you can see. And so, Vesper from Casino Royale, if you've ever seen the movie. But here's kind of a table if you want to screenshot this real quick. But you can see like two electron groups, three electron groups, four, five, six. Yeah, six actually quite a cool. I think this is like sulfur, maybe has like six. But anyways, for the most part, biologically, you'll see a lot of like molecules kind of have this like tetrahedral shape, and that's no coincidence. It's because most of these molecules are based off of carbon, and carbon is able to form four bonds, and so it's always going to have this kind of like tetrahedral geometry um, to these molecules. But yeah, any questions about Vesper? Is this worth memorizing? Like this table? No, I don't think so. I've never seen a USPO question about this. What's Casino Royale? It's a James Bond movie. Vesper Loki not useful. You don't need to memorize this, but just in case. Correct. Wait, I agree. I totally agree. Like this table is not worth memorizing because like you just like intuitively just like what is the best way to distribute out four like domains? It's like as a tetrahedron. But yeah. Okay. On the note of James Bond, bonds are biggest misconception I see, like kind of printed in textbooks and also like taught in just like school is that people say like energy is like stored in bonds, right? They're like, why are like, for example, like why are fats like high energy? It's because they have a lot of these carbon hydrogen bonds, and so there's energy stored in the bonds. I think this is like kind of true, but also like I think a little like it's a bit of a misconception because it actually takes energy to break a bond, right? So that's why I like think like bonds are like marriages. Right? It actually takes energy to get a divorce. It's very easy to fall into an attraction, but to actually like pull apart two atoms takes like significant energy, right? So like kind of the way to look at this picture is that these are like two bonded atoms, and if I wanted to pull them apart, you see that I need to invest energy, right? I need to invest energy to pull them apart. So you can imagine that as kind of like magnets, right? And so what does it actually mean when people say energy is stored in bonds? Energy is stored in the potential to form like new bonds, right? So this is a molecule of fat. And you can see that when we burn fat, we take in a lot of oxygen and we combine it with the fat to form like water and carbon dioxide, which are more stable products than the initial reactants. Right? And the reason why is that this carbon hydrogen bond is like pretty decent, but a stronger bond would be like a carbon oxygen bond or like an oxygen hydrogen bond, right? You can imagine kind of like if I have like a ball on like a shelf up here, like it's pretty stable up here, right? And it actually takes energy to lift it off of the table. But if I were to like then let it go and let it hit the ground, then it comes with a lot more energy. Right? So it actually takes energy to break the bond, but you gain back more energy from forming a new bond. Right? And so this takes us to the idea of Hess's law. And so what's happening when you're burning, for example, like from fat to like carbon dioxide, is you have to like you have to invest some energy to actually break the carbon hydrogen bonds, but you're going to get back more energy than you invested by allowing it to fall back to this like more stable rate, right? And so overall, like the total energy released from this reaction or like delta H or it's called enthalpy, but you can kind of think of it like potential energy, is like this just direct, like path independent, like from A to B. It doesn't matter like what path we go through. And so like A, first of all, this is kind of like just it's kind of like a law of the universe that like potential energy is like path independent. But B, this is more useful because if you want to like, for example, calculate how much energy it actually takes, or sorry, how much energy is released from burning a molecule of fat, you don't actually have to like measure this, right? You can just theoretically calculate if I were to take our reactants, go to some kind of intermediate and then calculate all the way back down to the products, then it actually works like this as well. But yeah, I think this may be a homework problem that you'll see this week. But yeah, what's the hormone joke? I don't know what hormone joke you guys are talking about. I have no idea what you guys are talking about. Okay. Next, we have reaction coordinate diagrams. You also see these in Campbell, but it's kind of another representation of like Hess's law, right? So you can imagine that along this x-axis, we have some kind of like imaginary like reaction coordinate, or basically like some metric of how like far along the reaction has progressed. Typically, like if you have a what's called a spontaneous reaction is one that releases energy, right? And so it starts with more energy than it ends up with, and so we're going to release this total amount of energy, but we may need to overcome what's called an activation energy. Wood doesn't just like spontaneously like combust by itself, right? You have to give it kind of a flame or some kind of source of ignition, right? And so that's basically you need to overcome this activation energy. And so what enzymes do, enzymes are catalysts. And so what catalysts do is they speed along reactions. They do this by lowering the activation energy barrier, right? So it makes it easier for this reaction to happen. But crucially, what's really important to know is that enzymes don't actually affect the total change in energy. Right, so I'll say it again. So enzymes and catalysts do not affect the total like change in energy. All they do is they lower the activation energy, which allows the rate to increase, right? So enzymes they don't make like non-spontaneous reactions spontaneous. All they do is make spontaneous reactions happen faster. Okay. Yeah, how do they lower the activation energy? That's a great question. There's a couple of ways for them to do it, but typically what they'll do is they will stabilize this like transition state. And so, for example, I don't know, you can imagine like an extreme transition state of like burning fat, right? Imagine we like separated all the carbon by itself and turned it into just like pure elemental carbon, and we had pure elemental oxygen, and we combine the two to make carbon dioxide. That's like a very extreme example of like a transition state. But typically enzymes will stabilize the transition state, which means that it has like less energy. Right. And so because there's less energy, it means this activation energy is going to be lower. What in the world is the hormone joke? I know the hormone joke, but I don't want to say it. Maybe off the recording, I'll say it. So I can't leave a bad impression for the new students, For all the returning students, it's perfectly fine, but for the new students, I don't want to scare anyone away. No, Aryan, that's a more advanced tech. We haven't gone to that tech yet, but that's the elite ball knowledge. Um, you're welcome, Kat. I thought I spent a while thinking of that one. I thought about that one. Anyways. Okay. You're welcome. You're welcome. You're never gonna forget. I remember when I read that in Campbell, I was like, "There's just no way. This is so obscure. Like, how am I gonna remember this?" And then like the mnemonic is like, "Great." Okay. This takes us to thermodynamics. Thermodynamics. If you're like a tryhard, you're gonna learn these three. But if you're a USABO student, you can ignore the last one. This one is just like a technical thing. It's just like a mathematical thing. It doesn't matter. And the second one also, like the first one, is like kind of intuitive. You know this, right? So really, the only important one is to know that like for spontaneous process, it means that the entropy is going to increase, right? And so this is the first definition that you're going to see of like kind of entropy and enthalpy in USABO. You have this equation delta G equals delta H minus T delta S. So delta G is what's called Gibbs free energy. Gibbs free energy is kind of I don't really know like the best, easiest definition for it, but the way you can kind of think of it is just like energy available to do stuff, right? Why it's called like free energy, right? Delta H is going to be the change in enthalpy. Enthalpy is kind of like the potential energy of like your reactants, right? So for example, like here, like delta H refers to the potential energy of like A versus B, right? And then delta S is going to be the change in entropy. Entropy is kind of like damn, I can't believe we got into this much. But entropy is kind of a property of the universe. It's kind of a measure of like the disorder of things, right? And so in general, if you're going to make more disorder, you're going to increase the entropy of the universe. So, for example, like if I have just like one book on like a table, that's like very easy, right? It's a very simple state. There's only one possible state, or maybe there's like a few states, like the book can be in like one place or not. But if you suddenly add like 10 books onto the table, there's a lot of different ways to order the books. There's a lot of ways you could like arrange the books, right? And so there's a lot of potential like arrangements of like the reactants, right? And so change in entropy typically is going to be positive when you add like more products than reactants. So for example, if you are producing like a lot of gas as like a byproduct, right? So I keep going back to this example, but you can see here we're starting with like one fat molecule and we're producing like all of these like carbon dioxide and water molecules. Or I guess you have these oxygens, but in total there's like 79 molecules on this side and there's like 107 molecules, right? So we're increasing the total number of molecules, so there's like more disorder in the system, right? And so we're going to have like a positive delta S. And if you have a positive delta S, and like temperature is always going to be positive because it's in Kelvin, you can never have a negative temperature. That means you have like a very strongly negative second term here, right? Which means that in general, your delta G is going to be negative. And so that actually takes us to, oh, whoops, sorry. Delta G is going to be negative for like spontaneous reactions and positive for non-spontaneous reactions. But yeah, in general, like only like negative delta G reactions can happen, but you can couple like a positive delta G reaction plus like a negative delta G reaction to get an overall like negative delta G. Okay. Um, um, this slide I've left in as a notion, as out of respect for Ian. Ian originally put the slide in. Now we're going to talk about water. I actually have no idea what this was. I was like flipping through my slides earlier and I had no idea what this was, but my girlfriend was looking over my shoulder. She was like, "Oh my God!" Like I remember I watched the show as a kid, and so apparently this show is about like these girls who like go into like a cave. And like when the moon, it was like a full moon or something, they like turn into mermaids when they touch water. So apparently that's what the show is about. So I have no idea. But yeah, I don't know. I never watched this movie. I never watched the show. Did anyone watch the show as a kid? Great. What's Udip's comment? That's insane, Udip. That's actually insane. That's insane. That's crazy. Okay, anyways, water. Okay, I feel like every time you teach one of these like honors bio or like AP bio level courses, it always starts with the four properties of water. Can anyone tell me what the four properties, or just like any of them are? Like popcorn. Oh, I forgot to do bow bucks. Oh, I'm supposed to do bow bucks. I totally forgot. Okay, I'll do bow bucks starting from next week. The bow bucks are our way to like kind of reward participation. So if you participate or you give like good responses, or when we have these participation moments, you can win bow bucks. And then you can exchange the bow bucks for great prizes if you accumulate enough of them, right? But yeah. Typically at the start of class, I'll appoint someone to like keep track of bow bucks. Usually it's Udeep, but I forgot to do that this week. I'll do it next week. No worries. Okay. Blah blah blah. I'm seeing a lot of people saying the right answer, so very proud of you guys. Cohesion, adhesion, I think are typically thought of as one, but yeah, cohesion, adhesion is a good one. High specific heat and evaporative cooling are kind of like related. Universal solvent. Thank you, Keshav. That's also known. And yes, William's song has the most elite ball knowledge one of the four, that liquid water is more dense than ice. Everyone always forgets about that one because it's kind of obscure, but like hey, like it is necessary. Anyways, okay, so first, water is like a very good solvent. That's actually why life like needs water as like liquid water specifically, because life is a lot of chemistry, and chemistry really only happens, or like only interesting chemistry happens in like these liquid states because things can like mix, and there's a lot of things to do. Water is capable of both very strong cohesion and adhesion. Water has a high specific heat, and ice floats on water. Yeah, where I put this picture, in. But that's exactly how I feel. I was like, oh my God, like one, two, and three, like these are bangers. These are some really good properties. And then they always put ice floats at the end. I feel like because it's like the stupidest one. But anyways, yeah. What is the triple point of water? Yeah. So the triple point of like any compound is like a specific type, like temperature and pressure at which like all three possible like states like are kind of like they intersect, right? And so like with very, very slight perturbations, you can go from like one state to another. Actually, I take that back. Not every compound has a triple point, because if you look at like a phase diagram, you have to have this intersection of all three points. And so some substances actually don't have triple points. But yes, like water has like a triple point. Yeah. Yeah. Sometimes you should have one, but sometimes you can have like weird things where it's like in the supercritical zone. So it's not like true, like I don't know. This is not a chemistry class. If you want to talk about more chemistry, I'm sure Joseph will be happy to talk about more chemistry. But anyways, okay. Strongly polar bonds. Water is a very strong solvent exactly because it has these strong hydrogen bonds, right? How does, oh, whoops. Oh, I thought it was the next slide, but because it has these strong hydrogen bonds, water is also like very sticky. It likes to stick to itself, right? And so that's what leads to what is called cohesion. So cohesion is the property of water to like adhere to itself, right? You can remember like co means like together, right? Like coexist. And adhesion is the property of water to like stick to other things. If you ever like I don't know had like if you ever had like a piece of plastic with like water and like stuck it to like another piece of plastic, there's kind of like this like strong like attraction between these two, right? And so that's like an example of like adhesion. On the biological scale, this is important because, for example, trees, like trees need to move water all the way down from their roots all the way to like the top of their crowns, right? And so if you were to ask like an engineer to do this, they would be like, oh, like I need these pipes, I need these pumps. I need like solar power to like power these pumps to do it. But trees are capable of doing this basically for free because they have these really small like channels throughout their trunk. And like through this process called capillary action, the water adheres to the sides of the capillary and also to itself. So you kind of have this like unbroken like chain of water molecules that evaporates at the top and pulls all the water up basically like for free using like the power of the sun. This also allows like some insects to kind of like walk on the surface of water. Water has a very high surface tension. If you ever did this like experiment in elementary school where you like put a ton of like water drops like onto a penny, you like know how strong the surface tension can be. Next, we got high specific heat. So water, again, because of these hydrogen bonds, to actually heat up like liquid water, it requires a lot of energy. Because you need to like break these like mainly because you need to like break these hydrogen bonds, right? Like if these molecules are moving faster, they're going to be bonded to each other like less frequently, right? And so you have to invest energy to break these bonds. And so you can heat water like you can put a lot of like energy into water without it heating up too quickly. This is important both at the like organismic scale because a lot of like organisms regulate their body temperature through like this water. And also when water evaporates, it's going to take like the highest energy like molecules first. And so that's actually what evaporative cooling is. It's when the like hottest molecules like come off, and so it leaves you like cooler behind. And so that's like why we sweat, for example. This is also important for regulating like global climate patterns. If you've ever noticed, if you're from like California, if this looks familiar to you, you can see that it's actually like a pretty mild climate because it's like next to the ocean, and so it has a lot of this like California should be a lot hotter than it is, but because it's like thermoregulated by like this large body of water, it makes it a lot nicer. But yeah. How many people exactly? Literally, I literally Googled like generic California like suburb, and like I swear I know like plenty of people who like live in like neighborhoods that look like this. But yeah, I agree. California, low-key chop. Not a fan of California. But yeah. Wow, this is bringing back so many memories from like high school chemistry. Like this is insane. But yeah. Okay. What is great? Yeah. What is heat? I said that you can invest a lot of energy, or you can put a lot of energy into water without actually like raising the temperature of heat. And so like, what even is heat? All right, doesn't matter. Outside the scope of this class, we don't talk about what heat is because we're biologists. We're not chemists. The last one is that ice floats. This is like really nice if you want to like have drinks, I guess. Like if you have drinks, the ice is like nice at the top. But also on the like, on the planet scale, this is important because when ice like freezes, it stays at the top, and that actually lets it like insulate the rest of the ice. Oh, sorry, the rest of the water below. If actually like ice was like less dense than, or sorry, was denser than water, you would have like the top would freeze and then would like sink down, and then the top would freeze again and then would sink down, and then everything would just like freeze over. So it's actually very important that ice floats. Also because ice floats, ice also reflects a lot of like sunlight, and so this also is like very important against like climate change. But yeah. Great. Oh yeah, why is ice less dense than water? Because water is like kind of disorganized. You can see it's kind of just like amorphous, and steam. Obviously, the molecules are very far apart because it's a gas. But in ice, because there's such little thermal energy, they can actually lock into this crystal structure. And it happens to be that for water, this crystal structure is less dense than this amorphous like water structure, and so that's why ice happens to be less dense. Yeah. People were mentioning this earlier in the, yep, okay, exactly. People in the chat. Water is most dense at 4 degrees Celsius. So, things that are cool, like, sorry, cold things like contract, right? So dense, like cold water is denser, but it starts to expand again once it goes below 4 degrees Celsius. So the densest water is 4 degrees Celsius. Yeah, that's actually what the measurement of it. If you ever have, here's like some EBK. If you ever have to do, actually, do they still have Fermi estimates? I don't think they have Fermi questions for Siley anymore. Oh, they still do. Okay, great. I love Fermi. If you ever need to know like the density of water, and that's actually where it comes from. Like 1 gram per cubic centimeter is actually measured at 4 degrees Celsius. That's actually the definition of a gram and a centimeter, I believe. Or is that the definition of gram or centimeter? I can't remember. One of them is defined based on this, but anyways, I think it's probably the centimeter, maybe. But yeah. Okay. Right. Ice also expands. This allows you to have like weathering, right? So if water like seeps into the cracks of like rocks and then it freezes, it's going to expand, and that can actually generate like a lot of pressure, enough pressure to break open rocks. And so this is also important, like kind of on the macro scale for like weathering and like geology and stuff. But yeah. Great. Okay, more water chemistry. How does water actually dissolve things, right? So water dissolve things because the attraction between the water molecules and the solutes is stronger than the attraction of the solutes to each other, right? And so, on the like actual interface between like a salt crystal and the water, this water is like peeling away each of these ions like one by one and forming what's called a hydration shell, where all of the like positively charged sides of the like hydrogen on the water is attracted to like the negative anions. And the negative, like oxygen side of the water, is attracted to the positive anions, right? And so, because this is like a more stable configuration, you can form more of these hydrogen bonds. It's going to favor having this like dissolved like ions in solution instead of this like strong like crystal structure. Yeah. This also is like why polar substances are able to dissolve in water, right? Whereas non-polar substances, because the non-polar substances can't form these dipole-dipole interactions, they're not going to like, it's not energetically favorable for it to dissolve things. And so this leads to the idea of like dissolves like, right? Polar substances will dissolve polar solutes, and like non-polar solvents will dissolve non-polar solvents. Because you want these like strong polar-polar interactions, like it's not favorable to have like polar non-polar interactions. Does that make sense? But if the ionic, yeah, if the ionic bond is like sufficiently strong enough, yes. But typically this is like, I mean, yeah, like that's actually what happens when you have what's called like a precipitation reaction. So a precipitation reaction is where you have like ions that are like soluble, but they form a new like substance that is no longer soluble, right? That's actually what happens when you're forming a precipitation reaction. Yeah. Yeah. Basically what Ajay said. Yeah. Why do nonpolar solvents dissolve nonpolar solids then? Like just in general, yeah, I mean exactly. Like not all nonpolar things mix, but in general, like you want to, it's like from like an entropy standpoint, imagine we have like, I don't know, 100 people wearing red shirts in like one corner and 100 people wearing blue shirts in another corner. It's just more likely for the blue people to like spread out, right? And so there's just like more macrostates where things are dissolved. This is like not even assuming that there's any like attraction between red shirts and blue shirts, right? And so in general, it's just like more thermodynamically favorable to have like dissolved, unless there's like some energetically favorable reason why you don't want it dissolved. Right. What is the precipitation thing I explained again? Oh, okay. So this is like it's a specific type of reaction in chemistry called a precipitation reaction. But basically, you can start with like two liquids that are like fully dissolved, and you like mix them together, and like the dissolved solutes inside of them like form a new product that is like insoluble. And because it's insoluble, it's going to fall out of solution, right? So that's called a like precipitation reaction. Yeah, it's a specific example of a double replacement reaction. Yeah. Why do non-polar things not mix with water? It's because like they could theoretically mix with water, but through mixing with water, like decrease the amount of like water-water interactions, right? Because now like imagine like let in this like toy example I had, let's say red shirts and blue shirts like don't care about each other. It's fine for them to mingle. But if the red shirts like each other more than they like the blue shirts, they'd rather like hang out with each other than hang out with the blue shirts, right? So they'd rather put the blue shirts into one corner. That's why they don't dissolve, right? Does that make sense? Great. Okay. Yeah, Loki, we're not finishing in time, but it's okay because I only wanted to get to like macromolecules, which is good enough. Okay. Now we've been talking about a lot of water chemistry. Let's talk about acids and bases. You definitely heard of like acids at least before. Maybe like you read about it in like some book. But bases are just like the opposite of acids. So what even is an acid? There's a couple different definitions of acids. You got like your like Lewis acids, you got your Brownstein-Lowry acids. But for the sake of Campbell, just know that acids are what are called proton donors. So for example, water is actually like a slightly like very weak acid, I guess. Because like two water molecules, they can like spontaneously dissociate, where it donates like one hydrogen to a hydrogen ion, which is basically just a proton, right? And so it can self-dissociate into what's a hydronium ion and a hydroxide ion. What pH actually is, pH stands for potential of hydrogen, but basically it's the negative log of the concentration of hydrogen in a solution. Right. And so pH of 7 is neutral, which means that if the negative log of the proton concentration is 7, that means the proton concentration is 10 to the negative 7. Right. So basically like 1 in 10 million water molecules will dissociate into like a proton and like a hydroxide. Does that make sense? And so if something has a higher concentration of protons than 10 to the negative 7, it's acidic. And if it's less than 10 to the negative 7, it's going to be basic. Right. So on the very strong scale, right? So pH goes all the way from like 0 to 14 theoretically. It is theoretically possible to have like what I call like super acids. So they actually have like negative pHs, and you also have like super bases, which are more than 14. But for the most part, like you'll see on this scale. And so whenever there's always this like balance between like hydroxide ions and like hydronium ions. And so always you're gonna have like the hydrogen or the proton concentration times the hydroxide concentration is going to equal 10 to the negative 14. Right. So for example, if you have like pH of 4, that means that the proton concentration is 10 to the negative 4, meaning that the hydroxide concentration is 10 to the negative 10. Right. Does this make sense? Does everyone understand like what acids and bases actually are? Like they're not just like these like strange things. Yes, exactly. Or like self dissociation. Like water has a dissociation constant. That's actually why it's like K like H2O is like 10 to negative 14. That's like what it means. But yeah. Yeah, KW. Yeah, there you go. Great. Okay. Buffers. Yeah, so usually like because you can see that like the pH scale like so sensitive, it's a logarithmic scale, right? Like if I just add like 1 mole of like protons to like a solution of like water, you can see that the molarity instantly goes like off the scale, right? And so if you add even like a tiny amount of like a very strong acid into a large amount of water, you can instantly change the pH by like several like units. I don't think, yeah, pH is like unitless. Yeah, several units, right? But if you have a buffer solution in the water, basically a buffer system is just a like donor acid and like a conjugate base. Right? And so when you add protons to a solution, the protons are going to be like picked up by the bases and they convert it into this like weak acid. And vice versa, if you add like hydroxide to the solution, it's going to take the protons away from the donor acid and it's going to be converted into the acceptor base. Right. So in biological systems, the most important one is kind of this like bicarbonate buffer system. But because we have this kind of like reservoir of like molecules that can accept or donate protons, it's going to be like resistant to these like very wide swings in pH. This is very important because like if your pH or like for example, if your blood pH changes like even like 1/10 of a unit, like you'll immediately have like some kind of like it could be like pretty bad, right? And so in general, you're going to want to have these like stable systems. And so basically everything in biology is going to be buffered. But yeah, any questions about this? Maybe we'll throw like some calculations related to like buffers and like acid base like on the homework. Why not? Yeah, I mean, like you might not die, but like you'll definitely feel it, right? Like here, like you'll definitely feel it. So what is a buffer? A buffer is like it's a buffer system. It's going to be like a donor acid and its conjugate base, right? Or like a weak acid and like a conjugate base. Conjugate base, and this is referring to like if you add a proton to it, it becomes the acid, right? So it's kind of like this interchangeable form, right? You may see them kind of like abbreviated as just like HA and like A minus, right? Where A just refers to like basically anything, right? Yeah, that's a buffer system. Yeah. What slide are we on? We're on slide 41. It's okay. I think as long as we get to slide like 60 or so, like I'll be happy. Anyway, okay. Carbon. Carbon is basically found in all the molecules that make up life. That's actually why like a whole branch of study is called like organic chemistry. It basically just means like the study of like molecules and chemistry involving like carbon atoms. So here's a picture of pasta. Pasta is made of carbohydrates. And so as the name implies, carbohydrates are made of like carbon and like water and stuff. Okay. I don't know why I put this here, but the Miller-Urey experiment was this experiment is this even in Campbell chapter 2? It might be in Campbell chapter 2. Maybe it's not. I don't even know. Oh, it is. Okay, great. That's why I put it in. That's why I put it in. Basically, it disproved the theory, or not like disproved the theory, people already knew. But for the longest time, people thought that like living things were living because they had this like immaterial, like special, like essence, right? And it's impossible to ever make like living things from non-living things. But they actually synthesized urea in like I believe like the 1800s. And urea is an organic molecule like produced by living things, but they're able to synthesize it in like non-living ways. And so this kind of broke down the idea that like there's anything special about life. And so the Miller-Urey experiment was kind of a experiment that wanted to like study where did the original like building blocks of life come from. And so they basically had the initial like starting like reagents that they thought might have been on like primordial Earth. So they had like hydrogen gas, like ammonia, methane, like very simple molecules. And they basically just like boiled it like for like a long time. They added some like electrodes, some like energy to the system, and they found that over time it was actually able to produce some like more complicated organic molecules, such as like amino acids and like some basic sugars and stuff. And so Great. What do you need to know about this for USABO? Just know that reducing atmosphere, one of the leading theories was that instead of having an oxidizing atmosphere that we do nowadays because it's like full of oxygen, they theorized that originally there was a reducing atmosphere in like early Earth. Um, Yeah, Loki, I don't think this is important for you, Spo. Maybe like I saw a question about this like maybe 10 years ago, but like never again. Great. Okay. I mentioned earlier, carbon forms four bonds, and so it has like a lot of different shapes it can form. And so for example, like methane, ethane, and like ethylene, most of the molecules are going to be kind of like this like carbon backbone with like other things like attached to it. Lots and lots of shapes. You can have different molecules that have the same like chemical formula, but two different structures, right? So for example, it's like butane. Butane versus like 2-methylpropane. They both have four carbons like in this structure, but you can either arrange it as like kind of this line, or you can kind of arrange it as like this T block, right? And so these molecules, even though they have like the same like constituents, they actually function like differently, right? Is this a new concept for you, Buzz? Huh? Didn't I say, yeah, Ari, I don't know how Aryan remember this, but yes, I remember like for USABO, like if you make camp, like they have you like fill out this form and they ask you like what's like your favorite science experiment, and like I was like a bum like freshman and I didn't know that many experiments. I was like, yeah, this is my favorite experiment. But anyways, yeah, the new Veritasium video, it's not an isomer actually, Zachary. It's not an isomer. They're allotropes. Yes, correct. Yeah, they're not different isomers. But anyway, okay. Yeah, don't worry about memorizing this shit. It's like not important at all. Okay. What are isomers? Isomers are like the same molecule but in different shapes, right? And so you can have what are called structural isomers. So that was the example I gave earlier. So there's like actually like structurally distinct. And we can also have slightly more nuanced isomers. You can have what are called cis-trans isomers. So single bonds, you can kind of imagine you can like rotate them, but double bonds, like you can't rotate double bonds, right? So depending on the way it's locked in, like you can see, I can either have like my thumbs on the same side, or I can have my thumbs on the opposite side, right? And because you usually can't like break this bond, this is what's going to be called like a trans isomer, trans because they're on different sides. And this is like cis because they're on the same side, right? And so this is like a cis trans isomer, right? You can also have like L slash like D isomers. You can also have like whatever. L slash D isomers are related to like chiral center. So for example, if you have like your right hand and like your left hand, they're mirror images of one another, right? But I can't like rotate or translate my like right hand to be identical to my left hand. Right? So it's the same idea with this molecule. You can rotate this, you can do whatever you want to it, but anything short of flipping it in four-dimensional space, you cannot turn the L isomer into the D isomer. And these are functionally distinct versions of the molecule. Blah blah blah. Enantiomers, they have actual biological differences. So one of the first things that is very interesting about them is that they can like rotate light. So for example, if any of you watch Three Blue One Brown, here's for, like from the video. But basically, if you like take water, or you take like glucose or just like sugar into like a pole of light, it's going to bend the light in like one direction, preferably, right? And depending on what form of sugar you have versus like L sugar versus D sugar, it's going to rotate it one direction or the other. Some other drugs as well. Drugs typically need to be like enantiomerically pure, right? So for example, ibuprofen, there's like the S form and the R form. The R form doesn't really do anything, but the S form is like much more strong. Same thing as like albuterol. I think this is an asthma medicine. Again, like only the R like enantiomer is like actually effective. When you synthesize things like inorganically in like a lab, typically you're going to get like a 50-50 mixture of these things, which is called a racemic mixture. If you ever see this in like a question, that's just what it means. But most biological systems, because they're made from these like enzymes in like one preferential way, you'll have like a much more pure mix of like one versus the other. Great question. Why is it S and R, not L and D? So L and D is just like one specific way of referring to two different isomers. This is related to what's called like the Fisher projection. You don't need to worry about this. Just know like S and R are kind of the same idea as like L and D. But yes. Correct, exactly. Yeah, it's like these are just like special naming conventions. It's like not worth knowing, I think. I've never seen this show up on USPO. But if you like chemistry, feel free to like check this out. What did Ian say? Ian said what? Okay, anyways, chiral centers. Uh I don't remember what this is about, but it's just Breaking Bad. I remember there's this one scene in Breaking Bad because okay, sorry. If you know what Breaking Bad is a TV show where the whole premise is there's like this high school chemistry teacher who like makes meth. But methamphetamine actually happens to be one of those substances that is like different depending on its enantiomeric form. Like one of them is just like I think it's just like one of them is like a prescription drug and the other is like the street form of like methamphetamine, right? And so they want to make like a enantiomerically like pure substance. But yeah. Anyways, so I'll give you guys a bit of an exercise for some like interactiveness. Can anyone? Oh, actually, first, what is a chiral center? I never explained that. That's on me. A chiral center is a carbon that is bonded to four different groups. All right, so you can see here it's bonded to like a hydrogen, like a carbonyl group here, a methyl group, and an amino group here, right? And so you can see that because there are four distinct groups, you can either have it in this like L form or this D form. Right? And so whenever you have like a carbon that is bonded to four distinct groups, it's going to be what's called a chiral center. So can anyone point out to me where the chiral center is on this molecule? These are the same molecule. I've just shown it to you in like two different representations. So you can either see it like drawn out like this, or like some chemists are lazy. They'll just like omit any like carbons. And also this O minus is just like deprotonated, but this is the same fundamental like great. There's no chiral carbon here, right? So you may be tempted to say that like this thing in the middle is a chiral carbon because this is carbon, but because it's double bonded to this oxygen, there's actually only three like distinct groups here, right? So it's not chiral. Okay, great. What about this question here? This is ethanol. This molecule, depending who you are, maybe this molecule is like very important to you or not. Great, exactly. So there's no chiral carbon here again either, right? Because like this carbon on this side here, there's three hydrogens, so they're all like identical, and then this like carbon on this side here, there's two hydrogens, so it's identical. There's only like three distinct groups. Okay, what about this molecule here? I know, right, Joseph? I put that one in just for you, Joseph. People were saying the left one. People were saying like the bottom carbon. What makes a chiral carbon special though? People can ask you questions about it on their like medical school exams. That's why it's important. Great, exactly. Yeah. So the left one is the chiral carbon. Again, remember this the right chiral carbon is only bonded to three distinct groups, right? So it's not chiral. But this fourth one here, there's this methyl group which is distinct, this hydroxyl which is unique, and this like R group over here. Plus, remember it's like bonded to a hydrogen. It's not drawn here, but remember there's a hydrogen here, right? So there's a secret hydrogen to this one, right? So it's also going to be chiral. Yeah. Does that make sense, to everyone? Exactly. The hydrogen isn't drawn here, but you have to remember that the hydrogen is there. Yeah, exactly. Hidden hydrogen, hidden hydrogen. Okay. All right, here's the last one I'll give to you guys. Where are the chiral carbon or chiral carbons on this molecule? How do you know when there's a hidden hydrogen? Great question, Jacob. There's always a hidden hydrogen if you can't see like if it's what it's bonded to, right? There's always going to be like you always assume that if there's anything omitted, there's a hydrogen stuck to it. Yeah. Great. Yes. Okay. So it's the middle one again. So you can see again here I've been nice to you. I've shown you the hidden hydrogen. But remember, just like off of this picture, remember that there's a hidden hydrogen lurking here. Oh, sorry. I guess this is the same figure. MB. I did not realize. My bad. Okay. Oh yeah. Typically, carbon is going to be a chiral center because carbon like will always bind to four different groups. But you can also have special cases where nitrogen and sulfur can be chiral carbon, or sorry, chiral centers. Right. To be a chiral center, you just need four distinct groups. Right? And so if nitrogen has like a lone pair and is bonded to three other groups, then this lone pair is like distinct from other three. Right. So there actually is a chiral center with nitrogen. Same thing as sulfur. So you can see chiral centers that are like non-carbon. Very interesting. Yes, a lone pair counts, right? Because you can imagine that like there's like different like arrangements possible. Okay. Functional groups. A functional group is just like, a shorthand typically like drawn in like molecules because you'll see it like over and over again, right? There's only a finite number of ways to like combine different elements. And so you'll see the same things over and over again. So like an OH group is going to be called a hydroxyl. The main thing to know is that these are polar because they have this like oxygen hydrogen bond. And everything with like a hydroxyl is going to be called like an alcohol, right? Not like alcohol in like the colloquial sense, but like alcohol referring to like a family of like structures. But yes, alcohol is in fact an alcohol. It's like ethanol specifically. Do we need to memorize the functional groups for USABO? Like, yes, but like not in the way that like you have to memorize it. Like you'll just memorize it from like knowing stuff or just like reading, right? Like, would I say that you have like the alphabet memorized? No, but you just know the alphabet because you've been using letters so much, right? So it just comes with practice. Next, we have a carbonyl group. A carbonyl is just like a carbon, like a double bonded to an oxygen on the side. If it has, it's called a ketone, right? Or like an aldehyde, depending on where it is in the skeleton. So sugars are examples of like ketones and like aldehydes. Next, we have a carboxyl group. Carboxyl is like typically going to be an acid. This like hydroxyl group on the side here can be like deprotonated, and that will form like an acid. So these are called carboxylic acids. We've got amino groups, which is just like a nitrogen with two hydrogens. These are found in amino acids. Why is there like a circle here? I don't remember. We have a sulfhydryl group. It's just a sulfur and a hydrogen. You got phosphate groups. This is like a phosphorus with four Oxygen is actually is just like a phosphate. This is just a phosphate, the ion like stuck onto something. Oh, whoops, and we got methyl groups, which is like a methane. Oh yeah, we've hit 9 p.m. So if you need to go, actually wait, this is where I wanted to stop. So we talked about all the chemistry. Next week we're gonna start talking about biological macromolecules. So there are 4 different kinds of biological macromolecules. You have the carbohydrates, the lipids, the proteins, and the nucleic acids, and basically like all living things are made of these like 4 compounds together. But yeah, that's all I wanted to talk about today. So I'll stop the recording here. Actually wait, I think I have do I have? No, I don't. Okay. Usually I like to put Q&A at the end of kind of like or not like a Q&A, but just like a suggestion box. So if there's any like content that you're like confused about or like want more clarification on, um, here you go. If you have any like things that like you want clarification on or like you're not sure about or you want me to talk about next week, I'll leave a like form for you guys, but I forgot to make it this week, so I apologize. I hope you guys all enjoyed our first class. Definitely make sure you remember to do the readings. Do the readings, do the readings. You need to do the readings before you come to class, or else you're not going to know what's going on. Typically, Kevin is going to lecture about stuff like way beyond the level of Campbell, so make sure you understand like the base material before you go to class. I'll stop the recording here, but yeah.